In the motion graph approach, we start with the source of input data, such as motion capture or simulation. We look for similar frames in the input data and transition between them using simple blend operations. However, for objects with very high dimensionality, it is difficult to find frames where all the degrees of freedom line up simultaneously. We relax this restriction by dividing the scene up into separate groups and allowing different groups to transition at slightly different times. The transition offset time for group I is called tau I, both here and in the paper. Here, we highlight each group as it transitions. In addition to increasing the probability of finding a valid transition, our method also diffuses transition errors in time, making artifacts less obvious, especially for systems whose dynamics are essentially stochastic. Unfortunately, allowing groups to transition independently can introduce interpenetration artifacts such as those shown here. Here, artifacts are highlighted with a red circle. We remove these transition artifacts by imposing non-interpenetration constraints, and solve the resulting integer programs using a novel randomized solver. On a basic level, our solver works as follows. Suppose we are transitioning between the motion shown on top and the motion shown on bottom. Here we have divided the scene into two groups, each with a tau value shown. This is the resulting transition motion. Notice that there is an interpenetration in the third frame. Now we begin the main solver loop. Our solver first randomly selects an interpenetration. It then randomly selects a transition offset tau I to change, which could affect this interpenetration. It randomly selects a new value for tau I and checks to see if the total number of interpenetrations has changed. If the total number has not increased, the new tau I value is accepted. Because there is still an interpenetration in the scene, the solver again selects a violated interpenetration, selects an offset, and samples a new value. Here, the interpenetration is fixed, so the algorithm is complete. Now we see the solver on a larger example. In this example, tau values are displayed vertically across the bottom. Red groups represent violated interpenetrations, and green groups represent fixed interpenetrations. Blue groups are in the kinematic clique, that is, the set of groups whose tau values could affect a particular interpenetration constraint. The first step of the algorithm is to check for interpenetrations at any time during the transition. Here, a horizontal bar represents checking for collisions in a particular frame. Notice that groups are marked as red when interpenetrations are discovered. Now the algorithm begins fixing interpenetrations using the randomized technique discussed earlier. Note that it does not perform a complete collision check every time it changes a tau value. Instead, it checks a small set of problem groups. This is because all pairs collision testing is expensive. Now, all known interpenetrations have been fixed, so the algorithm again runs an all pairs collision check. It discovers a new interpenetration, and so returns to the randomized correction phase. Now that interpenetration has been fixed, so it again runs an all pairs collision check. Because no collisions are found, the transition is accepted. Now we will look at some examples of transitions. For each example, we will show the transition twice. The second time, we will highlight transitioning groups in yellow. This scene consists of 20 irises and 284 blades of grass, comprising 547 groups total. Here we see 1,005 blades of grass. This is a closer view of the same scene. Notice the contact between blades of grass in the foreground. This banana tree has 32 leaves. Each of these banners has 100 flags attached. We can instance these throughout the scene. We can instance smaller iris models to create a much larger scene. Here we see 26,000 iris and grass clumps. Because the runtime cost is a single pointer lookup per clump, we are bounded by render cost, and use level of detail accelerations to speed this up. This scene runs at approximately 3 frames per second using hardware.